All right, so this is the second lecture on practical AI. All right, let's see where we are. We started off at the lower left corner with no AI knowledge. We are on our way to practical AI knowledge. And in the first session, we talked about what machine learning is. And today we'll focus on how machine learning works. Let's go over what we already discussed, just to review. And we discussed what ML is, and that's essentially learning from examples, telling a machine what to do without explicitly program it to do a particular task. That goes in contrast to traditional programming where you have to write explicit instructions. And I presented to you 3 examples of a machine learning project. And the first one was this image classification example, where you want to be able to look at an image and say if it's a cat or a dog. And the workflow is as follows. Step 1, you collect a lot of examples of pictures along with their labels, whether they're cat or dog. Feed it into this algorithm, let it learn that what about a picture makes it a cat or a dog. And once it's done with that, the next step is to give it a picture for which you don't have a label, meaning you want to know if it's a cat or a dog, and hopefully it will give you a correct prediction that this is a dog. Another example I gave you was for spam emails. Again, step number 1, collect examples of emails with known labels, which is whether they're a spam or not. Feed it into this thing, let it learn, and then step 2, you can give it an email that you like to know whether it's spam, and it will hopefully make a correct prediction that this, for example, is not a spam. The third example I gave you was about predicting the price of a house. Again, step number 1, collect examples where each row is one house and for which you have the area and the price, and feed it into this algorithm. Once it learns the relationships between the input and the output, then you can give it an input, which is the area of the house, and it will tell you a prediction of the price house, in this case $200,000. Now, these 3 examples were very different in their applications. One was housing price, spam detector, and image classifier. But they were almost identical in the way I described their flow. In other words, there is the recipe for machine learning that is almost independent of what you're trying to do with that machine learning application. So now I want to present to you this recipe, which I essentially repeated 3 times when walking through these 3 examples. So the first part of this recipe is that there are these 2 steps, 2 phases of machine learning. You have a training and you have inference. Training is at step 1, where you present to this algorithm examples of data with input and output. So here in the image I have 3 examples, but you may imagine we'll have thousands of examples. And once it learns from that, step number 2 is when you go and make use of this. That's called inference, where you give it an example input and then it will predict an output, right? Now, what is this robot? Let's look a little more closely at it. Essentially, you have a learning algorithm. So let me get my pen. All right. So in the training side, you have a learning algorithm that ingests these data, and it comes up with a model of how the inputs map to the output. And then once that model is learned, you just grab it, plug it into your inference, Now you can give it an input, and that model hopefully can map the inputs to outputs so it can make a prediction of what the output should be. Now, again, let's zoom in a bit more. What is that model, or black box or orange box in this case? Generally speaking, the model is a mathematical expression. It's a formula that takes input as argument, and the result of that mathematical expression is the prediction of the output. So let's look at this. Here, I replaced x and y, input and output with x and y, kind of like universally accepted notation, where x is the input. Here in this case, x is the input for sample number 1, y is the output for sample number 1, so on and so forth. And f of x, as you might imagine, just a mathematical expression that takes x as input. Now, if during inference, if you put x into this function, well, it comes up with a value, and that is a prediction of the actual y, or the output. The hat is the convention for the predicted value. So if this model is very accurate, if you give it x1 here, the y hat will be very similar, very close to y1. Now let's look even more closely at this mathematical expression. What does it even look like? In the most primitive form, it could be the equation of a line. And this type of model would be called linear regression model. So here I present to you the data from the housing price, where x is the area, y is the price, and each row is one house. Essentially what you do is you're fitting a line into this data, and then once that line is fitted, it makes good predictions of the price. Now you can use it for inference. Just put the x into this mathematical expression and get an output, right? So what I'm talking about is something like this. Here you have the x, or the area. Here you have y, or the price. And each dot is one training example, one of those examples that you provided during training. And once the training is done, you end up with this line that does as good of a job in fitting to the actual data as possible. Now, what is training in this situation? The training is essentially tweaking the values of W0 and W1. Essentially, when you start the training, you assign some random values for W0 and W1. And during the training process, all you're trying to do is to turn these knobs of W0 and W1 to find the line that best fits your data. And that's pretty much the recipe for machine learning. Now, speaking of this example, let me show you a training in action. Don't worry about any code. Just look at these data. Horizontal axis is the X, or area. Vertical axis is the price. Blue dots are your training examples, the data that you want to use for training. And like I said, you can start with W0 and W1 that are shown up here with some whatever value, random. But then as you train, which is an iterative process, we will get into it, the line gets better and better of a fit to those blue dots. Now watch this. At some point, it just can't get any better, so it stays there. But now look at W0 and W1 here. And you see that during training, the values get tweaked. Watch. Right? So this is a training process. So training, the objective of training is to make predictions that are as close to actual labels as possible, right? So let's look at that housing price again. Here I have 2 data points, but you could have many. X is the area, Y is the actual house price, Y hat is your prediction with that line function that you have. And what you're trying to do is you look at the difference between these two, right? This is the error, in this case 10. And you want to minimize it as much as possible. So when I say make the best predictions, what I talk about is that make these errors as little as possible. And you're going to have n numbers for errors for the n number of examples you have. So what we do in situations like this, we end up with this one number that we call loss. And that signifies how bad your model is. The lower the loss, the better. And that loss is essentially the mean or the aggregation, the average of all these error terms. In the example of these two, so you take a square of this plus the square of this, and then that could be your loss. You can divide it by the number of samples, but that doesn't really make a huge difference. What you're trying to do is to find W0 and W1 such that this total loss would be minimal. So in other words, the objective of training is to minimize loss. And this is a key concept in machine learning. You always try to come up with this loss function that I have here, and then try to minimize it during training process, right? So training, now we can be a little more concrete in our definition. Training is minimizing loss by tweaking model parameters. And by the way, that's a long way. We have come a long way from where we started. We started by saying machine learning is about learning from examples, which sounds kind of magical. But now that we're looking under the hood, it doesn't sound as magical. Essentially, what we're saying now is training is about minimizing loss by tweaking model parameters. And this is more accurate. But how? Now we know what training is, but how does it work? How does it know how to turn these knobs, or in what direction to turn them to minimize loss? There is this, I guess there are different ways, but the primary way, the way that deep learning works in majority of machine learning algorithms are set up is by gradient descent. And I'm going to talk about that next. So it just so turns out that if you plot loss against any of the model parameters, you're going to end up with this bowl shape or V shape, kind of V shape or U shape curve. Again, as a reminder, loss is that one number that represents how bad your model is. You want to minimize it. That's the objective of your training, to tweak all of these model parameters, W0 and W1, to minimize that. So what does that mean? That means find the W1 value at this point, because this is where your loss is at minimum, right? So you want to find out where this point is. And this W1 at this point is what you want. And then you will do a similar thing for W0. If you can find W0 and W1 at the point where the loss is minimum, you have completed your training. That is training. And now let me explain how this gradient descent learning algorithm accomplishes that. So you start with some random model parameters. Let's say random W1, and that's here, right? And you calculate the gradient at that point, and the gradient look like this red line. And this gradient, the slope of this line, tells you in which direction you have to change or update the W1 parameter. It's going down, so you can tell, hey, I need to increase my W because I'm going downhill. So you do that, another iteration. And now, again, you get the gradient still pointing down, but not as deep, or not as steep, rather. So maybe you will still take a step forward, increase W1, but not by a whole lot. you keep repeating that, you can tell you're reaching the bottom of this thing because the slope is decreasing. And then at the end, you'll arrive at that minimum point where the slope is essentially zero or very close to zero. This is gradient descent. This is similar or analogous to you being in the hills or in the mountains somewhere in the middle of night, pitch dark. You're trying to go to the bottom of this thing, and you don't have to know where the bottom is. You just need to take steps downhill wherever you are. And that's really what's happening here. This gradient descent algorithm doesn't even know where the minimum loss is, but it always knows in which direction it has to go. Where is the downhill? Where is the descent of that gradient? So that's the idea, right? Now I want to go back to that live action training of this data. And this time I want you to pay attention to loss. Here is 12.95, now 0.7, now 0.3, and essentially it stays there, right? So that's what the training is about. I'm gonna reiterate what I just said with a different visuals to hopefully give you that intuition one more time. Now, let's look at the iteration that I just showed you, where the model parameters get updated, the loss drops, and the model gets more and more accurate. In each iteration, here's what's happening. So you have a model, right? And like I said, W0 and W1 could start with some random value. You gave it the X or the input of your training data, make some predictions. Now, you take the predictions, you take the X, you take the actual outputs, feed them into this gradient descent algorithm to determine in which direction the model parameters W0 and W1 need to be updated. So you do that. You update W0 and W1 by a little bit. And now this model is different from what it was just a moment ago, because now W0 and 1 are a bit different from where they were before. And hopefully they're converging towards the optimal model. But you keep repeating this loop. And that's what was happening in the code example that I showed you. Let me walk you through this with some other visuals. Say I'm looking at the same example of price versus area, and blue dots are your training data. And say at time 0, your W0 is this, W1 is this. Could be random values. So you have this model, you have these x's, 1,000, 2,000, 2,000, I guess 300 and 2,500. Well, feed them into the model and get the predictions. That was the first step in that iteration that I showed before. And the orange dots are the predictions of the model for those x's, right? So you have the predictions now, you have the x's and you have the actual y's. With this information, you can use the gradient descent to update the W0 and W1. And to do that, here's what you do. First, you get the gradients of the loss with respect to each of model parameters, right? And step 2, you determine how much you need to update W0 and W1 based on their gradients, right? So here, in this case, the W1 has a negative gradient, which means you want to increase your W1, and that's what we did. And in the case of W0, the gradient is 1,000, which means you are way to the right-hand side of that U-shape loss function that I showed earlier. So you want to take a step back. And the size of that step is proportional to the gradient. If the gradient is very steep, you know you're very far from the minimum loss, so you want to take a larger step. Otherwise, you would take a smaller step. Right? All right, so these are the updates that you want to make, and you go and update the values. And now your W0 is going to change from 250 to 150 because that was your delta, and similarly for that one. And now you have a slightly different model but you do the same operation again. Get the gradients, get the updates, and then update the model parameters. Now you have a better model. And finally, you end up with a model that's as good as it can get. And from this point on, if you just keep playing that game, the line doesn't change, like you saw in my live example, right? So this is essentially how pretty much all these machine learning algorithms work, no matter how big they are. There are obviously nuances and clever tricks here and there, but the story doesn't change. And that story is that you have a model that maps input to the output, and that model is a function or a mathematical expression with a bunch of parameters. And that training the model is about tweaking those parameters to minimize loss or to minimize the errors. And we also learned the way you train them, the way you can tweak these knobs is by taking small steps towards reducing that loss. The final note I want to make here is, if you look at this housing price example, it might not be exciting because you know that, well, this might be too much of a toy example. In other words, you can't predict the price of a house based on its area. You could have houses that are same size but different prices, right? That's not a surprise. And then it may suggest that these models are not of value, but I'm gonna prove otherwise. Let's say X1 is the area, Y is the price, and that was the model that we worked with. Well, I could add another column or another feature. That's the terminology for it. Maybe this was area. Let me see if I can write like area. This is the number of bedrooms. Bedroom, right? And now you have two features, two pieces of information. And the model has just one new parameter to learn. The key idea is nothing changes in the algorithm in the way that in the recipe that I described. It's just that with the same algorithm, with the same methodology that you were optimizing for, well, you were updating W0 and W1 to minimize loss, you do that for W2 as well. And in a general case, you could have N features, you could have 1,000 features, and all that's happening is that this model is getting larger and larger, but you use the same recipe, the same algorithm to update all of this. And that's really where the power of machine learning comes in scaling of it. Maybe the core concepts are primitive and simple, but when you scale it, it gets more and more powerful. And now if you look back at this example of Zestimate, which is Zillow's price estimate, now you can tell, well, in our mock examples, we looked at the area of the house, but I could also look at the size of the building, the age, number of bathrooms, number of bedrooms, the school district, the crime rate, household income. And now if you beef up your data set, your prediction gets more and more accurate. And now imagine with that, you would be able to estimate the prices of all the houses in the US every day. And not only that, improve your model every day because there's new data that's coming in. And your model will start learning patterns that a human will never be able to identify otherwise. So I talked about under the hood of how this machine learning stuff work. But if you're a practitioner, you don't have to write any code for gradient descent or anything like this. What you see here is all the code you need to train and make predictions of a model. So let me describe or walk you through what I have here. This is an open source library for machine learning in Python. It is a collection of a huge number of algorithms. And what I'm saying is that import the gradient descent regression model from the family of linear models from sklearn, right? So you're importing it here. Next step, you make an instance of it. You start using it. So I imported it, but I haven't used it yet. Now I'm saying I want a model of this type. And the entire training is actually a single line of code. Fit and train are synonymous in the world of sklearn. Fit is essentially saying fit the model into this data, or you can say train it based on this data. These are all the inputs and these are all their labels. And when you run this, what's happening is that your model, which has a bunch of parameters, W0, W1, start tweaking those two such that when you feed it X into that line or to that function, the predictions are as close to the actual labels as possible. And that's when the training is done. Final step, you want to make predictions with it. All it takes is to run model predict method. And this X could be whatever input you have. It could be an area of 1 house or 10 houses or whatever. It'll make predictions. So the API is pretty simple, but it's good to have that intuition about what's going on under the hood. I hope that was useful.